Hello guys, today we're gonna start with lecture 7. I know I told you we're gonna start with Boolean algebra in lecture 6, but I don't know, I thought if we take floating points now it's much better, so I decided to give this as a floating points. Let's see. So we took how to represent what? Integers. We took how to represent negative integers, the what? Sign representation, one's complement and two's complement, and we took how to represent characters. So today we're going to take how to represent floating points, or as you know, decimal points, which are what? A number with a decimal point, with a fraction. This is 0.5, which is half, 1 over 2, multiplied by what? 0.25, which is 1 over 4. Those are floating points numbers. Today we're going to take how does the computer understand them. How do we represent them to the computer so it can understand it. We have what's called scientific notation. This is one possible way, and we have the scientific notation where we have a radix of 10 for decimal. So 0.125 equals what? 1.25 multiplied by 10 to the minus 1. How's that? Let's use the pen now. Then, and we say here multiplied by what? This is 10 to the power 0. What's 10 to the power 0? This equals 1. And if you multiply anything with 1, it doesn't change anything. So 1 multiplied by this, it didn't change it. But why is it here minus 1? Because we moved the decimal point. This is called a decimal point or a floating point. We moved it one place to the right. So if we move right, we subtract. If we move left, we add the exponent. So if I moved it till here, if I had 0, or let's say 0.0125 point, and let's put a 0 here, that 0 doesn't make a difference, 0.25, what will my exponent or radix be? It will be 10 multiplied by 10 to the power 1. We add if we go left. Here's another example. We have what's this? 5 million equals what? 5.0 multiplied by 10 to the power 6. 10 to the power 6 is what? Is a million. So what we're saying is we're multiplying 5 multiplied by a million, which is 5 million. Here, what are we saying? We're multiplying 1.25 by what? By 1 over 10. Here we're multiplying it by 10. So let's see. Numbers written in scientific notation have 3 components. This component and this component, the radix, the mantissa or the significant, and the sign. We have it if it's positive or negative. Those 3 parts, and this is what we're gonna cover today. That's why we need it in what? Scientific notation, so we can represent it to the computer. Computer representation of a floating point number consists of 3 fixed sized fields: sign, exponent, and significant or mantissa. Those we assign a number of bits for each one. We're gonna cover 2 models. The IEEE 754 single precision model. It's a 32-bit model, and we have a 64-bit model, which is IEEE 754 double precision. Double is double the range. And if any, I think most of you took programming. What we mean by the IEEE, it's the float. We took in C or C++, and the 64-bit is the double. Remember, a float is what? How many bytes? It's 4 bytes. A double is double the amount, which is 8 bytes. And this is 4 bytes, 8 bytes. So we have 32 bit to represent a single precision. 1 bit is for the sign, negative or positive. 8 bit for the exponent, the 10 to the power whatever we have it when we represent it in scientific notation. So this is 9. We have 23 left for the precision. That's why they call it precision, how precise the number is. When I add more bits, my number is more precise, more accurate. In the double we have what? 1 for the sign, 11 for the exponent, which increased our range, and 52 for the precision or accuracy, which increased our precision. So let's see. I have 1.0. This is the 1th place. What would we have then? We have the 10th. Then we have the 100th. 1,000. 10,000. 100,000. We add, we keep adding a 0. Why? Because it's decimal. Now what if we go to the right? What do I mean by going to the right? We have 1 over 10. 1 over 10. And why is that? This is what? 10 to the power 0, 10 to the power 1, 10 to the power 2, 10 to the power 3. And here what do I have? 10 to the power minus 1. Go right, we subtract 1. 10 to the minus 2. 10 to the minus 3. So if this was 1 over 10, which was 0.1, 10 to the power minus 2 equals what? 1 over 10 or to the power 2, which equals 1 over 100. And what about 10 to the power minus 3 equals 1 over 10 to the power 3, which equals 1 over 1,000. And here we take them this 100, and here we took those with them, this, and this. So in binary, what do we have? 2 to the power 0. What do we have here? 2 to the power 1, which is 2. 2 to the power 2, which is 4. 2 to the power 3, which is 8. 2 to the power 4, which is 16. If I go to the right, 2 to the power minus 1, which is what? 1 over 2, which is half, let's say. And this would be 2 to the power minus 2, which is 1 over 4, which is what? 0.25. 2 to the power minus 3, which is 1 over 8, which is 0.125. And here they are. 2 to the power minus 1, which equals what? 1 over 2 to the power 1, which equals half. Then we have 2 to the power 2, which equals 1 over 2 to the power 2. This is negative 2, sorry. And equals a fourth, and then this 0.25. We have 2 to the power minus negative 3 or minus 3. It's going to be 1 over 2 to the power 3, which equals 1 over 8, which equals 0.125. So let's see, we've got those. Remember those, look at them. We have 0.5. Here we had what? When I tell you convert binary to decimal or decimal to binary, we're gonna put, remember I showed you the way 1, 2, 4, 8, that's the positional notation. 16, 32, 64, 128, 256, 512. This is the same way. But here what did we do? This 1 over 2, this 1 over 2 multiplied by 2, this 1 over 2 multiplied by 2 multiplied by 2. So each time we're dividing by 2. On the right of the decimal point, here we're multiplying by 2. 1 multiplied by 2 is 2, multiplied by 2 is 4, multiplied by 2 is 8, multiplied by 2 is 16, multiplied by 2 is 32. Here what's happening? We're dividing by 2. I have 1 divided by 2 is 0.5. divided by 2 is 0.25, divided by 2 is 0.125. So if I divide it also by 2, it's going to give me what? The next number is going to be 0.625. If I divide this by 0.3125, and we keep going. I don't think it's good. You should remember, but don't memorize it. As understand it. Start with 1, divide by 2, and keep dividing by 2. It'll be much easier for you than memorizing it. So we said this is, see, this is 2 to the power negative 4, which is 1 over 16, which is 0.0625. So now let's see how we represent floating points. Let's say we need to represent this to the computer. There's 3 steps that we need to do to convert this to what? Binary. What binary? I need to take one of the previous models. Am I gonna implement it as a float, the IEEE 754 single precision, the 32-bit, or am I gonna represent it as a double, the 64-bit, the IEEE 754 double precision? We'll do both, and that will matter at the end. It's not going to affect our calculation now. So what's the first step? First step is to convert this part to binary. We're going to convert all of it to binary, but let's take the 99, because this has a way and this has another way. So convert to binary. We're going to convert the 99 to binary. How do we convert it? Either we divide by 2 and take the remainder and read it from bottom up, or we do the 1, 2, 4, 8, 16, 64. That's the easiest. So 99, I have 64, yeah. And what else? Do I have 32? Yes. I have 96 now. How much is left? This is the way I do it. I'm left with 3, so 2, 1, and those are going to be zeros. I have a 2 and I have a 1. So this is my binary 99. We got it. Now what about the 0.625? We took the 0.5, 0.25, 0.125, 0.0625, but not 0.625. So what do we do here? Do we have a 0.5 here? Yes. So I'll take that as a 1. And let's see. And there's 2 ways. We divided it this way. I have a 0.5. I'll take a 1. Do I have a 0.25 left from what? 625 minus 0.5 equals 125. So I don't have 0.225, so this is 0. Do I have a 0.25? Yes, that was the answer. So I'll have 1 here, nothing's left, 0. I like to do it this way, but I think most students, until they get used to it, they like to use the other way. Don't forget this decimal point here. Let's see, this 0.5, 0.25, 0.12. We finished our number here. It's not necessary to put the 0, but usually I like to start with 4s, and I don't give more than 4 in any of my exams or quizzes. If you understand this, that's good. So now let's go to the other way. What's the other way? It's, I think, easier for people doing it the first time. Let's see how. We have 625, yeah. Okay, 1 minute. They took the number. Now we're gonna do it. We take the floating point part, or the fraction part. We multiply it by 2, or we add the same number. Either you put 0.625 or multiply by 2, whichever one you want. Now what does this equal? This equals 1.25. 50. So what can I do with it? I'll take this one as one of the binary, the first binary. Now I'll multiply. Now this is gone. Now I'll multiply again by 1. See, I took this one as my binary. I multiply again by 2, or I add 0.25, which equals what? 0.50. I added them, and I here, what did I do here? I added, and here I'm doing the multiplication. I'm doing it in 2 ways also this. So what do we take? We take the 0, put it in our binary number. Now what do we do? Again, either multiply by 2 or add 50. 0.5. What do we have? 1.00. We take this one up here, and what am I left with? Zeros. Then I stop. When you get zeros, you can't multiply, you can't add anything. So this will be the 625. But don't forget the decimal point. So there's 2 ways, whichever one you want to apply. It's good, but it's good to know them both. Going back to our example, we converted it. Here's my binary 99, and here's my fraction part. Now are we done? Can we represent it in a, let's say, a 32-bit model? No. Let's see what. 9.65 equals this. It also equals what? This. I didn't change. Just think. Same. I didn't move them, but I added what? Multiplied by 1. Does it change the equation? Multiplying by 1? No. Adding 0, it doesn't change. Multiplying by 1, it doesn't change an equation. And 2 to the power 0 is 1. So now we said if we move left, what do we do? Decimal point, we moved it from this place to this place. We add to the exponent 1. So this equals this. Moving decimal point 1 digit left. Now we move it left again, equals this. We move it left again, it equals this. All those, they have the same value, which is this. They're the same number. Going to what? Going to 6, moving it to here. They all have the same value. Remember, where did that happen with us? In the sign representation, what did we have? Negative and positive 0. 2 different representations. And here, how many representations we have? So many representations we can have. So now we need to standardize. We need to have one standard. I need to say, okay, we're going to take this standard as our standard, our normalization, or this, or this, or this. So we're going to have a base to decide which one we're going to take. First, and let's say I didn't bring that here, but first they started with 0.1 as a format for picking the numbers. So all the numbers, so in the previous old version, we'll take the 0.1100101101 multiplied by 2 to the power 7. So my exponent 7, and my minister is this. Oh, sorry, not that one. In the new version, they said no, we want to take what? 1 point. This is called the normal number. Normal number. And did they gain anything from that? Yes, because this you don't include it in the bits, so we gained an extra digit. And keep it in your mind. I don't want to confuse you now and complicate it, but I'll go over it when we get to it. Now, what about if we went to the right? Those all representation were going with the decimal point left. Going to the right, we're also gonna what? See all those different representation which are equal, all of them. That's why the problem, too many representations. So we need, this leads us to second step called normalization or standardization. I need to standardize, and we pick what? The 1 point. And remember, I said in the previous one, the old version, we had the xxx, this meaning what? The rest of the number. And for our example, we're going to take this as our standard or normalization, and those are not x. 1 point x x x x x, whatever we have. So now which one is normalized? This one, we said it's this one. Now this leads us to second step. Okay, same thing, which is this one. Okay, going back to that slide. So what was the first step? Remember what was the first step? Converting to binary. We converted this to this. Second step, we normalize or standardize. We pick what? We move this decimal point to this, so I'll have a standard, my standard format, and I'll have 1.0, all that number, 1.1, and all those numbers to the power 6. That's normalization. I have one standard. Now was that enough? No, I said we have 3 steps. The third step was what? The biased exponent. And what do I mean by bias is, think of it, the 2's complement. What did we do in the 2's complement? What's the 2's complement? A 2's complement is dividing my range. Half to negative, half to positive, so we can represent what? Negative numbers. Here what do we need? What if my exponent was 2 to the power negative 6? So in the, let's say in the IEEE 754, where I had 1 bit for the sign and 8 bit for the exponent and 23 for the precision, how am I gonna represent the negative 6? I'm gonna need to represent it in the 8 bit, but how am I gonna take the sign representation, meaning am I gonna take those 8 bits, I'm gonna take one as the sign and the other 7 left for the range. That's not good because I already have one sign bit here for the number sign, so we don't want to confuse stuff. Can we use words? Sorry, can we use one's complement or 2's complement? We use something similar to it. That's why they call it a bias, or let's say the offset from the original point. And here's how it's representing both negative and positive exponent. And how can I represent both negative and positive exponent? I divide my range. Let's say, for example, I have this number to the power negative 5 and 5. How am I going to represent that? If I told you to represent 5 in binary, it's easy. You're going to tell me 1, 2, 4, 8. So this is going to be 1, 0, 1. And I can have what? This is 8. Considering it 8-bit. So now if we want to represent the negative 5, how am I going to represent it? They came with the bias, and which model will affect why? We're going to see in a minute. Let's say we're doing it on the 8-bit exponent. 8-bit for the exponent. Now what's my range in an 8-bit? It's 2 to the power 8, which equals what? 255. I'm gonna divide half of my range negative and half of them positive. So my range is gonna be from negative 127 to 0 to 128. I can have 255 representations with 8-bit, or let's say 256. Range will be from 0 to 255. 0 is a number, so this will be my range. We're gonna include the negative numbers. But how can we include the negative numbers? Now what about if I took the other model, the double precision, where I have 11-bit for the exponent? My range, or how many things I can represent in 11-bit, what does it equal? And this is a really easy way. I always think of 2 to the power 10. You should get used to those. I like to know 2 to the power 10, 2 to the power 20. This equals 1024. Oh, sorry, 1024. So what's 2 to the power 11? I multiply this by 2, so it's going to be 2048. So I have 2048 representations, but I divide half of my range to negative and half of my range to positive. So we'll go from negative 120, 1023 till 0 till 1024. That's for the double precision, and that's how my range doubled. My range doubled. So now by the exponent here, how to represent negative 5 in 11-bit. Here I gave a simpler example. I didn't give the 8 because I want to show you something. In 5 bits, how many things can we represent? 2 to the power 5, meaning what? 32 things. So we said we have from 0 to 31. So we're gonna take what? We need negative 15 till 16. Why? So I can represent negative numbers. What are we gonna do? We add 15 to the exponent, positive or negative, meaning negative 15 plus 15 equals 0. Any number we get with this negative 15 exponent, I add 15 and I represent it as 0. So now 0 equals negative 15, same as the 2's complement. Negative 14 equals 1, I represent it as 1. Negative 13, I represent it as 2. Negative 12, I represent it as 3, and so on. So now my range was from what? Using 5 bits, I had from 0 to 31, and from 0 to what? What do you think? Negative 15 equals 0. Negative 14 equals 1. Negative 13, here is going to be what? Negative 1. And this, let's say 0 is negative 15. And this is going to be equal to what? Or should be 14. 15 is going to be what? On the range. 15 plus 15 is going to be 30. So after negative 1, we start with 30. Then what? Or sorry, 16, 31. We have the 16. Then we have the 15, 30. Or it's going to be, oh no, sorry. This is the 31 is 16, 30 is 15, and what about those? What's 15? 15 is 0. I took it the other way around, so this is 0. This is how I represent 0. 0 is going to be equal to 15. A 1 is going to be equal to 16, and that's by adding what? The 15. So if I had an 8-bit exponent, what do we do? My range is 2 to the power 55, 2 to the power 8, sorry, which is from 0 to the power 56. And we need negative and positive numbers. Do we add the 15 to the positive? Yes, sure. Yes, so now biased exponent, we represent the negative 5 plus 15 is going to be equal what? 10. Now let's see the exponent 11. And why did I put an x here? Plus 10 or 5 plus this is not what we want. This is just, I don't know, I think I put it because saying this is not what we want. We want what? The 11 exponent. We don't want the 5-bit, but this is right. Don't think this is wrong. Sorry about that. X. So I have exponent of 11. This is what? The 64-bit model, the double precision or the double. And we have the 32-bit, which has what? An 8-bit exponent. An 8-bit exponent. 5-bit exponents we add 15. 6-bit exponents we add what? 31 to the power 6 is what? 64. 2 to the power 7 is 128. How many we add? We add 63. So on. So 8 bits, how many do we add? Is there a relation between those? It's going to be 2 to the power 8 divided by 2 minus 1. 2 to the power 6 divided by 2 to the power 6 is 64. Divided by 2 is 32 minus 1 is 31. Exponent 5 to the power 5 is what? 32. Divided by 2 is 16 minus 1 is 15. That's how we decide the bases. So for an 8-bit exponent, it's going to be 127. For an 11-bit exponent, it's going to be 1023. And here's what we did here. Look at this. We have my 2 to the power 8 gives us 256. Divided by 2 is 128. Minus 1 is 127. Now here, what did we say 2 to the 11 was? 20. 48 divided by 2 is 1024. Minus 1 gives me 1023. That will be my bias. Back to our example. Biased exponent. We got this 1 point. We normalized. Now using the biased, which model are we gonna pick? Are we gonna pick the 32-bit model? We're gonna pick both of them. So we'll have what? 1 point single precision, and let's say how they represent it here. Here we're going over the 3 steps again, and we're gonna show now what. Let's go here back. So this is gonna be this 1.000111101 to the power 6 multiplied by 2 to the power 6 plus what? 127. If I'm using the single precision. If I'm using the double precision, it will be 6 multiplied by 1023. So let's see. We first step convert to binary. We convert it to binary. Then we normalize. We have one format, one standard, because we have too many representations, and that's not with the good with computers, because that causes confusion to them, and we don't want that to happen. Bias exponent, where we divide array into what? Half positive, half negative, so we can represent the negative number. We didn't have step 3, we can't represent negative numbers. So now the exponent is what? 133. Why? I had 2 to the power 6 plus 127. We add either 15, either 31, either 63, either 127. 6, here's the 6. 6 and 127 equals 133. This now I'm representing it. So 133 equals what? This in binary. The sign is 0. The precision. Now depending on how much bit I have. How many bits do I have here? I have 3, 6, 9. I think 9. 1, 2, 3, 6, 7, 8, 9. So I'll have my 9 numbers here. Is it 9 or 8? It's 8 numbers. So which one is missing here? Is it there missing or where? I can't. So here we have sign for the other one, the double precision. We have sign here 0. This is considered as 0. Oh, here I forgot the double precision I was talking about. We have 8 plus what? 15 zeros. So I'll have what? This. Here's the 15 zeros, and here's the 8 digits. Why? Because we have to represent it in 23 bits. We have to represent it in 23 bits. And the double precision, I have the sign 0, exponent 2 to the power 8 is going to be 1023 plus 6 equals 1029, and we can have a precision of 52 numbers. If you get a 1 or 2 at the beginning, the rest will be zeros. Don't freak out for the result. So now hopefully this was good. This was briefly what's floating point. It's really important, I think so. You need it. We're going to take some operations, and I'm thinking now of a really good program. Let's see if you remember it when we go to the programming part, and let's see if it's going to be useful. If you have any questions, please leave them in the comment or email me. Okay, I'll give you my email next time. I have you can use either Gaith Albadarin at my .unt.edu, or you can use my Google account, which is Gaith Rodan I think at gmail.com, which is assigned with the channel on YouTube. So now tomorrow we're gonna start with Gates. Gates is gonna be easy. I'm gonna give you simplifications. I'm gonna give you K-maps. Why not? It's a long holiday, so it will get you busy for a while. And in a couple of days I'm gonna start this is what I'm thinking. I'm gonna give you C and C++ together. C and C++ together. One screen will open the C++, and the other screen I'm gonna go over programming again. And so maybe after a month we take the advanced. If you think it's not a good idea to take assembly and C++, please leave me a comment. I'm flexible with that, or we can post the video. Whoever wants to see us here, if you're busy you can, but we need it for the advanced C++. Oh, sorry guys, that was the cup of tea. So I'll see you tomorrow. Thank you and have a great day.